Good day, everyone. I'm Arvin Enriquez, your subject teacher in General Mathematics. With this video lesson, we're going to discuss the topic solving exponential equations and inequalities under your General Mathematics from Quarter 1, Module 18. Our lesson objectives. At the end of this video lesson, you are expected to identify the properties used in solving exponential equations and inequalities, and solve exponential equations and inequalities. So here, solving exponential equations and inequalities. Anything that increases or decreases rapidly is said to be exponential. You have learned in the previous module that there are a lot of real-life situations involving such conditions. For instance, population growth, exponential decay, and compound interest. So these are real-life situations wherein we can apply the concept of your exponential function, exponential equation, and or exponential inequalities. So please do take note that the inverse of your exponential is your logarithmic. So it's the same thing wherein we can apply your logarithmic function, your logarithmic equation, and your logarithmic inequalities. So it's the same thing on how we apply these two concepts, no? Because they are inverse of one another. So the inverse of your exponential is the inverse is your logarithmic. The inverse of your logarithmic is your exponential. So in these situations, depict that so-called exponential functions. So in this population growth, exponential decay, and compound interest, so we apply your exponential functions. That's how we deal with your exponential functions, because there is an involvement of your two variable involved, wherein there is your x, that will be your independent variable, then your y is your independent variable. So meaning to say that we can see the relation, no, between your two variables involved in your population growth, in your exponential decay, and in your compound interest. So recall that an exponential function with base b is a form of b f of x is equal to b raised to x, or y is equal to b raised to x, where b is greater than 0 but b is not equal to 1. So as long that there is an involvement of your two variables, no, that is your x and y variables, your x being your independent variable, then your y being your dependent variable, we need to satisfy again that your b is greater than 0, that your b is not equal to 1. So if your b is equal to 1 half, it's fine because it's greater than 0 and not equal to 1. Because 1 half is equal to 0.5, it's greater than 0 and not equal to 1. So have you noticed anything with the exponent? How does it differ from the exponents of some other functions? No? You can assess and to check, no, the exponent of your exponential function, there is an attachment, oh, and that is your independent variable x. Your independent variable x, once you are dealing with exponential function, you will always see, no, that your variable x will be on your exponent. So here, no, if you know that, that's good. So the exponential function has exponents that are variables. Yes, it is, no, that is your x variable, because your base is just a number, then you cannot put a variable on it, no? So in the past lesson, you have learned that this exponent determines how fast a function increases or decreases. Yes, it is, no, because this exponent pertains to your x variable or your independent variable. If your x increases, it's automatic that the function also increases. Or if your x decreases, it's automatic that your function decreases also. But there are times, no, when your x or your exponent increases, there are times wherein your y decreases. So it's depend on how we deal with your variables and your numerical coefficient for that particular function. So it really depends, no? What I'm trying to point out here is that whatever values that we're going to put as a value of your exponent, it will affect, no? It will affect the the value of your function y or f of x. So there is a change, no, in your for the value of f of x or y if there is a change in your exponent. So here let's deal with solving exponential equations. So one-to-one property of exponential function state that f of x is equal to b raised to x. If x sub 1 is not equal to x sub 2, then b raised x sub 1 is not equal to b raised x sub 2. Once you are dealing with your exponential functions. But now, in your exponential equations, no, conversely, if b raised to x sub 1 is equal now to b raised to x sub 2, then x sub 1 is equal to x sub 2. So meaning to say, if your b1 here, for example, if your b1 and your b2 here are equal, no? That's why we always need to make sure that your b1 is equal to uh, b2 or base 1 to base 2 for us to uh, assume or to conclude that your exponent 1 is equal to exponent 2. If base 1 is not equal to base 2, then we cannot assume or we cannot conclude that x sub 1 is equal to x sub 2. That's why there are times, no, or there are situations wherein we need to convert a certain base. Or for example, we need to convert base 2 to make it equal to your base 1. And for that note, no, we can conclude that x sub 1 is equal to x sub 2. Your exponents are equal if and only if, no, your base sub 1 is equal to base sub 2. No? In this statement, we can only assume that x sub 1 is equal to x sub 2 if b1 is equal to b sub 2. No? Please do take note of that. This property paves the way in understanding how to solve exponential equations. So for example, so let's apply this one, no? Your example number 1. So solve for the value of x in 4 raised to x plus 1 is equal to 64. Now, here, as you can see in your base 1, you have a base 1 here which is equal to 4. Now, how can we express this 64 if we're using a base 4? So what will be the exponent of 4 that can give us 64? So you need to look for an exponent of 4 that can provide you a value which is equal to 64. Now, since 4 raised to 3, so that will be equal to 4 multiplied by 4 multiplied by 4, or that will be equal to 16 here. 16 multiplied by 4, that will be equal to 64. So we're going to express a certain part, no, of your equations for us to make no that your b base 1 is equal to base sub 2, so we can assume and conclude that your x sub 1 or your exponent 1 is equal to x sub 2, which is your exponent 2. Now, we can express now, no? As you can see here, it was being stated that 64 as 4 raised to 3 for both sides of the equation to have same bases. So one-to-one property of exponential functions state that if b raised to x sub 1 is equal to b raised to x sub 2, then x sub 1 is equal to x sub 2. So here, your exponent here, no? Since we have the same bases here, your b sub 1 is 4, then your b sub 2 is also 4, then we can assume that x plus 1, your exponent in your base 1, is equal to your exponent in your base 2, which is equal to 3. Now, using the concept of the addition property of equality, we can transpose, we can transpose this positive 1 to another side of your equation from positive value to a negative value, or we can just simply subtract both sides, of your equation by 1 for us to cancel out this 1 here and to subtract 1 in another side. So why we need to subtract both sides of your equation? Because for us not to violate any rules in math. Because in your original equation, there is no such thing as negative 1 in your left side. So if we put negative 1 in your left side, it is our task, to put negative 1 also to your right side for us not to violate any rules in math. So our main goal now is to look for the value of x. So the value of x now is x is equal to 3 minus 1, which is equal to 2. So our final answer for this example is x is equal to 2. So for example number 2, solve for the value of x in 3 raised to 4x is equal to 9 raised to x plus 1. So as you can see, there is a 3 raised to 4x, 3 being your base 1, 4x being your first exponent or exponent in your base 1. And if you try to look at your base 2, which is equal to 9, 9 is divisible by 3. Now, since 9 is divisible by 3, what is the exponent of 9 that can provide us, what is the exponent of 3 that can provide us a value of 9? So here we can express 9 as equal to 3 raised to 2 because 3 multiplied by 3, that will be equal to 9. So for both sides of the equation to have same bases. So our main target here is to have a sides of equation having the same bases. We really need to make sure that base sub 1 is equal to base sub 2 for us to conclude that your exponent 1 is equal to your exponent 2. Now, in this case, we copy your left side, then we express your 9 using your 3 raised to 2, then we copy your exponent x plus 1. So here, as your exponent in your 3 that can provide you a value of 9, we're going to distribute these two to your x plus 1. Next thing to do is to apply again the one-to-one property of the exponential functions. So it's the same concept. So since base 1 now is equal to your base sub 2, we can conclude that your exponent 1 here is equal to your exponent 2. So we distribute 2 to your x, that's why it's 2x, then 2 to 1, that's why it's 2 here. Now, next thing to do is to apply the addition property of equality to solve for the value of x. Now, in this case, we can transpose this 2x to another side of your equations from positive to a negative value from the right side going to the left side of the equations, or we can subtract both sides, no, by negative 2x for us to cancel negative 2x in the right side of your equation. Or we just simply put all your x variable, no, all your terms that has an exponent that has a variable x, no, to another, to one side of your equation. So that's why we're just putting all your terms, no, with your variable x to the left side of your equation. Or we can apply the addition property of equality by simply subtracting, no, both sides of your equation by negative 2x. Now, since 2x and negative 2x will be cancelled here, so 4x minus 2x is equal to 2x, then we copy your positive 2. So we combine like terms. Yes, it is, no, we combine like terms because 4x and 2x are like terms, no? So use the multiplication property equality by multiplying both sides of the equation by 1/2. Or it can, we can divide both sides, no, by 2 for us to cancel your numerical coefficient here in your left side of your equation. So if we divide both sides by 2 or we multiply the entire equation by 1/2, it's the same result. We can cancel your numerical coefficient here because that is equal to 1. So we don't need to put your numerical coefficient which is equal to 1 here. So 2 divided by 2, that will be equal to positive 1. So that's how we deal with this one. No, what I'm trying to point out in solving an exponential equation, you need to express, no, both your base 1 and base 2 on the same manner. Meaning to say that your base sub 1 must be always be must be equal to your base sub 2 before we conclude that your exponent 1 is equal to your exponent 2. So let's now deal with how we solve exponential inequality. So recall that in exponential function, no, it's the same concept with your exponential equations. The only difference that the symbol, no, that exists between your left side and right side of this inequality and or your equations. In this inequality, the sign is that it shows or it represents inequality between your left side and right side. So that's the only difference, no, in your exponential equations. So it's the same thing, no? Once we apply the concept of your exponential function, that your f of x is equal to b raised to x, wherein your b is greater than 0 and your b is not equal to 1. So now, the key to solving exponential inequality is the fact, no, that if b is not equal to 1 and x sub 1 is greater than to x sub 2, in this case, no, your b is greater than 1 and your x sub 1 is greater than to x sub 2, then bx sub 1 is greater than bx sub 2. So that's how we see it, no? Otherwise, if 0 is less than b is less than 1, so meaning to say that the value of your b will fall in between your 0 and positive 1, then your bx sub 1 is less than bx sub 2. So you need to satisfy this condition before you conclude that your bx sub 1 or b raised to x sub 1 is less than your bx raised to b raised to x sub 2, I mean. So let us further make this clear by considering the next examples. So for us to visualize more, so what these concepts bring to us, no, can bring to us, I mean, no, then let's deal now with your example number 3 for us to see how can we apply the conditions being given. So for example number 3, solve for the values of x in 5 raised to x is greater than 125 raised to x plus 8. So first thing to do, it's the same process with your exponential functions. So we need to express, no, both sides, and to have the same values, no, of bases. So that's why we're going to express this 125, no? What is the exponent of 5 that can provide you 125? And that is equal to 3. Now, we can express this 125 as 5 raised to 3 because 5 raised to 3, it's 5 multiplied by 5, it's 25 multiplied by 5, it's 125. For both sides of the inequality to have the same bases. Now, if that is the case, no, we can conclude that in this one, if your b is greater than 1, as you can see here, if your b is greater than 1, you need to satisfy this condition. Since 5 is greater than 1, then we can assume that x sub 1 is greater than x sub 2. So we just simply use, no, the condition being given for us, no, when your b is greater than 1. That's why your x here, we copy your exponent here, x, then we copy your exponent in your second base, which is 3 multiplied by x plus 8. So we distribute your 3 to x plus 8, so it becomes 3x plus 24. Since 5 here is greater than 1, no, we satisfy the condition. So we can move forward with this part. Now, your b, it is a fact, no, that if b is greater than 1, b raised to x sub 1 is greater than bx sub 2, wherein your x sub 1 is greater than x sub 2. So that's how we see things, no? So use addition property of equality to solve for the value of x. Now, no? So as you can see in your original inequality, you have x here and 2x plus 24 here. What we need to do is to transpose this x to another side of your equation. We really need to make sure, no, that the value or the terms, no, with your variable x will be on the one side of the equations. Meaning to say, we really need to rearrange the inequality, and we need to put all the terms, no, with variable x to one side of this inequality. Then those constant or numbers, no, without a variable attached to it, then we need to put them to the another side of the equation. So since we need both, no, both your left side and right side, no, there is a change both in your right side and left side. So we need to transpose x to another side and 24 to another side, no. So we need to apply the addition property of equality since they are both positive numbers, positive x and positive 24. So we need to subtract negative x and negative 24, no, minus 24, I mean, for both sides of your inequality for us to cancel your, for us to transfer your positive 24 to another side and positive x to another side of your inequality. So since here, x plus minus x will be cancelled, so we copy your negative 24 here. In this case, we cancel your positive 24 and negative 24. Then 3x minus x, it becomes 2x. So both sides are divisible by 2. So it can be negative 2x now is greater than x, as you can see here. Negative 12, I mean, because negative 24 divided by 2, it's negative 12. So negative 2x divided by 2, it's x. So here, negative 12 is greater than x. Or we can rewrite this one, no? That your x is less than negative 12. Since negative 12, no, in our resulting value that negative 12 is greater than x, then we can provide the idea, no? Since negative 12 is greater than x, it's automatic that your x is less than negative 12. So we arrive in this resulting value by simply applying your multiplication property of equality by multiplying both sides of the equation by 1/2. Or we just simply divide both sides by +2. So hence, the solution to the exponential inequality 5 raised to x is greater than 125 raised to x plus 8 is the set of all real numbers less than 12. Meaning to say, the value of your x here is less than -12, so it will start from -12, no? Less than -12. So there's a limit here, no? Less than -12, so it can be -12.25, no? Negative uh, 12.5, no? As long that is less than -12, up to your negative infinity here, no? All your values, no, of your x will be less than -12. So meaning to say, all real numbers, no, which are negative, which are less than -12, that is the value of your independent variable in this exponential inequality. So that's how we look, no, for the value of your variable x, and that's how we deal or solve for this exponential inequality. So for example number 4, solve for the values of x in 1 over 7 raised to 2x plus 9 less than or equal to 1 over 343 raised to x minus 5. Now, first thing to do is to make sure, no, or to convert, if your base 1 is not equal to base 2, then we need to look for the bigger value. If the bigger value is not equal to your smaller value, definitely it's not. No, we need to express this bigger value. It's the same manner to a smaller value of your base. So since 1 over 343, there's a bigger value in your denominator here. 343 is greater than 7 or bigger than 7. So we can express this 343 as 1 over 7 raised to 3. So for both sides of the inequality to have same bases. Because our main goal first is to make your base 1 equal to your base sub 2. No? Here, we can express 1 over 7 raised to 2x plus 9. Here, this will be your 1 over 7 raised to 3. That will be equal to your 1 over 343 raised to 1 over 7 raised to 3 multiplied by x minus 5. So since here b1 is equal to 1 over 7, it is in fact that if 0 is less than b less than 1, or your b or the value of your b, since 1 over 7 is less than 1 and greater than 0, then it falls, no, it falls in between your 0 and 1. So we can assume, no, we can assume that your b raised to x sub 1 is less than b raised to x sub 2. Then there's a typographical error here in your modules. So it is x sub 1 less than your x sub 2. So if we satisfy this given condition, we can conclude that your b raised to x sub 1 is less than your b raised to x sub 2. Then x sub 1 is less than x sub 2. So in this case, no, there is a typographical error here, so that will be less than or equal to. It's the same thing here, so we need to correct first, less than or equal to. So it's less than or equal to. Then we continue. So we apply the addition property of equality to solve for the value of x. So in this case, no, in this case, we are here, no, to correct some typographical errors and to solve for the value of y. So here, we apply your addition property. So we need to subtract, we need to consider, and to make sure, first, we need to put all your terms with variable x to one side of your inequality, then all your terms without a variable attached to it to another side of your inequality. So that's why we really need to apply your addition property of equality, or we subtract, no? We subtract negative 2x plus 15 both sides of your equation, then 2x minus 2x will be cancelled, no? Then 9 plus 15, it's 24. Then negative 15 plus 15, it becomes 0. Then 3x minus 2x, so that will be equal to x. In this case, 24 is less than or equal to x. So we can say that x now, that x, there is a typographical error here, that x is greater than or equal to your x. So we combine like terms, no? Because 2x minus 2x are like terms. 15 and 15 are like terms. That's why we need to combine them. So we arrive with the idea, no? In this case, there's a typographical error in this part, no? So it becomes x now is greater than or equal to 24. So this will be our final uh, values, no, in your inequality. So thus the solution to the exponential inequality 1 over 7 raised to 2x plus 9 is less than or equal to 1 over 343 raised to x minus 5 is the set of all real numbers, no? Is the set of all real numbers that is greater than, no? It's greater than or equal to 24. So in symbols, no? So still there's a typographical error here that will be x greater than or equal to 24, or it start from positive 24, no? So it start from positive 24 to a positive infinity, because your x can be greater than 24 or equal to 24. Meaning to say that the value of your x here will start from 24, positive 24, going to your positive infinity. So that will be the final answer for this one. So for your activity, so find the missing x. So you just simply apply whatever we discussed, no, the conditions being given, no, then we need to solve for the value of x. So your task now is to solve for the values of x for each of the following exponential equations and inequalities. Here, there's a equation, inequality, equation, inequality, and equation. So there are 3 equations here and 2 inequalities. So find the value of x, then you can put this one, your solutions and answer, no, in your Cattleya notebooks. So thanks for watching. Please do like and comment and subscribe.